Yeah, so now we learned a little bit about single component or pure component phase diagrams, and we'll use that learning once we discuss what's the most relevant for us, which is multi-component systems, which is what we find naturally in nature, at least petroleum systems. Um, Important for me to note this, probably should have noted this earlier. So most of the slides that we're going to go through in this course is actually made by one of my great friends and colleagues here at Whitson, Bilal Yunus, and hopefully you will see much more to him if you take some of the other classes on Whitson Academy, or taking, for instance, the advanced PVT and EOS fluid characterization course, which is also available on this platform. Um, we'll recap on a couple of things that we emphasized with the reservoir fluid classification when it comes to PT diagrams. And the reason is this is one of the things, the few things maybe that it's worthwhile hearing a couple of times just to make sure that it's 100% clear. Because if this is 100% clear, your world will be much more simple, and your understanding hopefully will also be better of these concepts. Again, a little bit nicer drawing than what I drew by hand a little bit earlier in one of the previous lessons. However, the principles are the same. When we talk about a multi-component system, we have what's called a phase envelope many times, where everything within this envelope is two phases and everything on the outside is a single phase. Related to this, we typically talk about a critical or a Krekkonen bar, which is the maximum pressure where there's actually a saturation pressure. So it's the tangent on this on the pressure axis, and then we have this a similar concept on the temperature axis, which is called the Krekkonen term, which is similarly the same, the highest call it tangent pressure to the two-phase region. Inside of the two-phase envelope, we have these quality lines, sometimes also called equal volume lines. Many different names for this, but it's simply representing call it conditions where the relative volumes is constant. For instance, we have 80% liquid and 20% gas. And again, just re-emphasizing where we have both oil and gas, and where we have either single phase oil or single phase gas. Very good. So now we're going to reiterate on a couple of these reservoir fluid classification items. And we are now including a little bit of additional complexity. So we'll, in addition to looking at the PT diagram, we'll also look at the liquid relative volume plot associated with each of these diagrams. And just for the sake of these illustrations, this is just a given mixture. That it can, for instance, be 40% methane and 60% decane, normal decane. And it's this is a binary mix, but it's just a mix of different components. And this particular liquid relative volume plot that I was talking about is the plot that we see here. Yeah, and it's just defined as the volume of oil divided by the total volume at that particular pressure and temperature. So let's say we start like we have some starting conditions around here. We then deplete through a depletion process, which is what we do most of the time when we produce a reservoir. Reservoir pressure goes down until we reach the two-phase region. And in this region, we know that since it's a single-phase liquid, we have a constant liquid relative volume. We know there's only liquid there, so the VRO should be 1. Then below, in the two-phase region, we get a relationship that's linear. And we mentioned this earlier for a particular type of reservoir fluid, which is black oil. Okay, and that's also why when we plot this, the temperature here is temperature TBO. So this is a black oil. This is the black oil system, and this right here is what we call PB. So which is the bubble point pressure. Taking this a step further, but a similar type of exercise. Now we have shifted the temperature a little bit. We're at a higher temperature, as we see right here, and we'll do the same exercise, and above the saturation pressure again. We're again talking about a bubble point right here. The liquid relative volume is constant, so it's only liquid there. So that's fair. It's 1. But below, we see that we get a curve that's not linear, but it's actually non-linear, or it has a little bit of a bend in it. And that's what, at least internally at Whitson, what we, in a strict classification, we would use that as one of the criteria to define something as a volatile oil. Now again, as we did for the reservoir fluid classification case, we have now gone from a temperature that's on the left side of the critical temperature to be on the right side of the critical temperature. But just important to emphasize that we're still between the TC and this TCRI, which is the critical or Cree-Con term. That means that we, by definition, as we talked about earlier, that we've already gone through, we have a gas condensate reservoir, and above the so-called dew point, PD, we know that the relative oil volume should be 0 because there's only gas there, which we see down here. But what happens is that once we drop below the dew point, actually condensate comes out of solution, and we start to actually build a oil saturation or a condensate saturation. And that curve looks like what we see right here. And it's a gas condensate. And we will discuss why this curve goes down, actually turns and becomes non-monotonic right here a little bit later. What's important to emphasize is that before the call it minimum, this is a condensation-driven process, while when it turns, it actually becomes a vaporization-driven process. And once we start to talk about K values, that's when we actually will start to get an understanding of why this is the case. Good. And now we have moved to a temperature that's even on the outside of the Cree-Con term, or to the right of the Cree-Con term. In this particular case, we actually will always have a reservoir gas phase. And once we always have a reservoir gas phase, the VRO, so call it the oil saturation or the relative oil volume, will be 0 all the time. So that's what we see here. So kind of boring. What's important, as we talked about earlier, is also that wet gas, for it to be defined as a wet gas, the surface process right here has to be in the two-phase region. So we have to produce condensate and we have to produce gas for it to be for it to qualify as wet gas. If it does not, if the surface process is outside of this two-phase region, so the phase envelope, it's actually characterized as a dry gas, which would be the case here, where we have surface conditions that is outside of the two-phase envelope, and the relative oil volume in the reservoir is still 0, as we see here, so the same as for wet gas. Here, that's kind of why we do also a separator optimization or facility design and whatnot to maybe optimize or try to actually get this particular point right here inside of the two-phase region. And why do we want to do that? Well, the reason for that is that liquids are worth more than gas. So one way to, for instance, get this particular point into the two-phase region would be to put on a freezer and lower the temperature. What will happen then is that we'll get we'll eventually get into the two-phase region. We'll have both gas and condensate producing at the surface, but then we'll actually have something that's redefined to be a wet gas reservoir. And we'll make much more dollars from our well, hopefully. Good. So last, but just also to reiterate on some of these things, let's just because what we did now was that we changed the temperature from each of the cases, right? Well, now we'll try to change essentially the composition. So we have fixed the temperature, okay? The idea that we went through now is that we actually had a fixed composition. And a fixed composition, as we saw in the first slide, is essentially saying that, okay, here we actually have a fixed, sorry about that. Then we are going a little bit far, yeah. So what we're essentially saying then is that the PT diagram is constant. So when we're talking about one composition, the PT diagram is the same for that composition, okay? But instead of having a fixed composition, we'll now fix the reservoir temperature and we'll actually change composition, which was one of the introductory note about fundamental understanding that we mentioned before. Okay, so going back here, so now we fixed reservoir temperature, that's constant, but we'll mix two different products that, you can think about this as a separated oil and a separated gas, and we'll mix that into different ratios. In this case, we can just simplify and we can think about a vapor-like component, for instance, methane, and mixing that with something that's oil-like, for instance, normal decane. Normal decane, the vapor pressure curve for normal decane is printed right here, and for methane it's printed right here. If we make a mixture of the two of them, we'll get a phase envelope looking, for instance, something like this. Here we've mixed it in a ratio where we only have 10 mole% of methane, and almost everything is decane. So as we should expect, we should be far from the critical point, and we should have essentially a system that's an oil system, probably a very low GOR type of oil. So the black oil classification will then be around 100 to 1,000 scf per barrel. Here we like to be very strict in how we use it. So we typically actually write stock tank barrels in general. If we add a little bit more of the gas-like component, we see that the critical point is moving closer to the reservoir temperature. And that's what we typically define as maybe a volatile oil, where the GORs is between 1,000 to 2,500 scf per barrel. And once we've actually added so much gas that the critical point is to the left of the reservoir temperature, then we are actually talking about a gas condensate system, or something that's very, very near critical. So this is actually a near critical gas condensate system. But for practical purposes, when things are this near critical, we in general just call it a near critical system. Again, adding more gas, we'll get something that can be classified as a gas condensate. We talked about this before. Some of the ranges that we have here, they are a little bit arbitrary and rule of thumb based, but this can be good starting points. But as we remember, the definition of a gas condensate, the strict definition, is not defined by GORs. The strict definition is determined that you have a gas phase in the reservoir that actually exhibits a dew point, so at reservoir temperature. Okay, so if that's not the case, you're not dealing with a gas condensate reservoir, no matter what the GOR is. Okay. So and if you continue to do this exercise, you might end up with a phase envelope that's actually outside of the initial reservoir temperature range. Then we're talking about a wet gas reservoir, and again, if you do this even further, you're eventually is going to end up with something that's essentially dry gas, which might have a very high GOR. So yeah, it's like the GOR is essentially infinite, and the money you make from the oil or condensate there is you can almost neglect it. It won't be of any importance.